Today, we will talk about an extraordinary event that allows me to closely observe one of the most mysterious and fascinating particles in the universe, neutrinos. The CMENET collaboration has detected an ultra-high-energy neutrino, the most powerful ever observed so far. This extraordinary event offers us the opportunity to explore one of the most enigmatic particles, difficult to study yet fundamental for understanding the secrets of the universe. In events like this, neutrinos reveal themselves as almost invisible particles, challenging to study because they interact very little with matter. They have an infinitesimal mass, possess no electric charge, and interact only through the weak nuclear force and gravity. This particular characteristic makes neutrinos almost indifferent to matter. They can pass through the Earth, the Sun, and even entire galaxies without being stopped. Every second, billions of neutrinos pass through our bodies without us noticing, without us perceiving their presence. It is precisely this mysterious and invisible nature that makes them unique tools for observing the universe. Their rare interactions with matter make them perfect for exploring extremely distant and inaccessible places, such as the cores of stars or the farthest regions of the universe. But what can they really tell us about the cosmos, and what does the discovery of an ultra-high-energy neutrino imply? Let's explore these questions together. The history of neutrinos is fascinating and full of surprising discoveries. They were first theorized in 1930 by the Austrian physicist Wolfgang Pauli, who sought to explain an apparent violation of the principle of energy conservation during radioactive decay. However, Pauli himself was not convinced of their existence, calling his intuition a desperate move. Nevertheless, in 1956, an experiment conducted by physicists Clyde Cowan and Frederick Reines confirmed their existence, opening a new chapter in the history of physics. From that moment on, neutrinos changed our way of understanding matter and the universe. Neutrinos are common particles in the universe and can be produced in numerous contexts. They are generated inside stars, around black holes, in supernova explosions, and even on Earth, in nuclear reactors. An example of neutrinos coming from our star is solar neutrinos, which allow us to study the Sun's core. Since neutrinos are not stopped by matter, we can directly observe the nuclear fusion processes occurring inside our star. This has helped confirm theoretical models explaining how the Sun works and produces energy. Moreover, there is a sort of cosmic neutrino background, neutrinos produced in the very first moments of the universe's existence, which could provide us with incredibly valuable information about the primordial cosmos. These neutrinos, originating during the Big Bang, can offer fundamental insights into understanding the origins of the universe itself. There are also neutrinos arriving from violent cosmic events, such as supernova explosions or collisions between black holes, with energies far exceeding those generated by particle accelerators. These neutrinos are extraordinary messengers of what happens in the distant and invisible universe. The main obstacle to studying neutrinos is that they interact very rarely with matter. To detect them, it is necessary to build extremely sensitive detectors capable of capturing even the weakest traces of these particles. Additionally, it is crucial that the detectors are placed in extreme locations where noise from other sources, such as radiation or particles, is minimized. For example, some experiments are conducted underground, like the famous ice cube experiment in Antarctica, while others have been placed in deep-sea locations where water can shield against other radiation. CMENET, or the Kilometer Cube Neutrino Telescope, is one such experiment. It is located in the Mediterranean Sea, at depths ranging from 2,500 to 3,500 meters below sea level, an ideal environment for reducing environmental noise. CMENET's detectors consist of thousands of sensors sensitive to a particular form of light called Cherenkov light. When a charged particle, such as M1, is produced by a neutrino interaction with matter, it can move faster than light in water, producing radiation known as Cherenkov light. Although nothing can exceed the speed of light in a vacuum, in certain materials like water, the speed of light is lower than in a vacuum, allowing a charged particle to generate a trail of light that can be detected by sensors. CMENET's long vertical strings, mounted on the seafloor, host spherical optical modules with sensors that detect and amplify these weak light signals. The telescope is spread across multiple sites, including one near Sicily, called ARCA, and one near France, called ARCA. It was specifically ARCA that detected the ultra-high-energy neutrino we are discussing. Now, let's get to the heart of the matter. The observed neutrino has an extraordinarily high energy of 220 petaelectronvolts, BeV. To give you an idea, this energy is about 100 million billion times greater than that of visible light and 30 times higher than any other neutrino ever observed. The event occurred on February 13, 2023, but it took over a year to analyze the data and confirm the validity of the results, as events like this are extremely rare and complex to decipher. What could the detection of a neutrino with such incredible energy mean? Most likely, the neutrino originates from an extremely violent cosmic event, almost certainly located beyond our galaxy and at enormous cosmic distances. The extraordinary energy of this neutrino suggests that it may have been produced by a blazar, an active galaxy with a supermassive black hole at its center, or it could be the result of a gamma-ray burst, an explosion of highly energetic radiation. It may also have been generated by the interaction of cosmic rays with the cosmic microwave background radiation. What is certain is that this discovery represents a significant step forward in neutrino astronomy and multi-messenger astronomy. Multi-messenger astronomy is a growing field that seeks to combine information from different cosmic messengers, such as light, gravitational waves, and, increasingly, neutrinos. This will allow us to explore the universe more comprehensively and deeply than ever before, combining observations from different cosmic languages to paint a richer and more detailed picture. Neutrinos, despite being elusive and difficult to detect, are extraordinary and powerful messengers. Thanks to experiments like MINIT, we are getting closer and closer to understanding the cosmic mysteries that surround us. And this discovery, like many others to come, is just the beginning of an exciting journey through the universe. If you enjoyed this video, leave a like, subscribe, and turn on notifications so you don't miss future videos.